1 light year sounds like nothing. Astronomers barely pause on it. But behind that single unit hides 9 trillion kilometers of vacuum and a wall built from the hardest limits physics allows. Every technology humanity has ever built, rockets, nuclear engines, laser arrays, falls short by thousands of years. So, how long would it actually take us to travel 1 light year? Before we start, a gentle subscribe helps this channel keep growing. Now let's begin. Humans have always done this. We name things to tame them. The ocean, a word, 7 letters. It fits inside your mouth in less than a second, rolls off the tongue like it costs nothing. But the ocean is 136 quintillion liters of water, pressing down on everything beneath it, cold and black, and absolutely indifferent to anything alive. The word does not capture that. The word was never meant to. The word exists so we can talk about the ocean without being paralyzed by what the ocean actually is. We did the same thing to the universe. 1 word, 8 letters. We say it at dinner tables, in classrooms, in documentary titles, in casual conversation. We say it the way we say weather. And somewhere in the act of naming it, we convinced ourselves we had measured it, contained it, made it manageable. And then we did it again. With a distance so extreme it should have no name at all. We called it a light year. 1 light year. Clean. Compact. A single unit. It sounds like something you could find on a ruler, if the ruler were just a little longer. Textbooks introduce it in a single sentence and move on. Science documentaries use it as a stepping stone toward more impressive numbers. Millions of light years, billions of light years. Treating the single light year as barely worth pausing on a rounding error on the way to grander. Scales, that is the trap, and almost everyone falls into it. Here is what 1 light year actually is, written out completely without abbreviation, without scientific notation, without any shortcut that lets your brain skip over the magnitude. 9,461,000,000,000 kilometers. Read that again, not the digits. The words, 9,461,000,000,000. That is the number of kilometers contained inside a single light year. Not a particularly impressive light year, not a record-breaking one, just one. The smallest standard unit astronomers use to measure the distance between stars. Now here is the problem. Your brain just read those words and filed them under a category it uses for all numbers beyond a certain size. The category has no precise boundaries. It is simply labeled very large, unimaginably far, a lot. Neuroscience has a name for this. Researchers who study numerical cognition call it the compression of large magnitudes. The human brain evolved to count food track distances walkable in a day, judge how far a predator stands from the edge of firelight. It never needed to distinguish emotionally between 1 million and 1 billion. Both are just more than you can hold. Both trigger the same internal response, big number, move on. So when you read 9,461,000,000,000 kilometers, your brain does not collapse in awe, it does not calculate, it does not truly register. It simply stamps the number with the same label it uses for every other figure that exceeds what the human body can experience far away, and it moves on. That stamp is the most dangerous thing in this entire story, because it turns a distance that should stop you cold into something you absorb without friction. You read it, you nod, and 30 seconds later, you are thinking about something else entirely. The number passed through your mind the way light passes through glass. No resistance, no weight, no memory. And that is exactly how 1 light year has spent decades hiding in plain sight. Not because people are unintelligent, not because the information is unavailable, but because the human brain is structurally incapable of feeling the difference between a number that is merely enormous and a number that is cosmically, categorically, life-alteringly beyond anything our species has ever touched. Does your brain truly feel the difference between 1 trillion and 1 billion, between 9 trillion and 900 trillion? If you are honest with yourself, the answer is no. They are both just very far. They both live in the same mental drawer. That drawer is where 1 light year has been sitting, quietly, waiting, completely misunderstood. And to understand it for real, not as a string of digits, not as a label in a textbook, not as background noise in a documentary, you have to stop using words and numbers entirely. You have to start with the only language the human brain was actually built to process. Images. Scale. Something you can see. Start with a single fact and do not rush past it. Light travels at 299,792 kilometers per second. Not approximately, not roughly, exactly. This number is not a measurement with error bars. It is not an estimate that better instruments might someday revise. It is a defined constant, a fixed value written into the International System of Units as permanent and non-negotiable as any number in all of physics. The speed of light is not something the universe does. It is something the universe is. Now take 1 second, a single tick of a clock, the gap between one heartbeat and the next. In that 1 second, a beam of light does not merely cross a room or a city or a country. In 1 second, light travels far enough to circle the entire Earth 7.5 times. Not once, 7.5 times. While you blink, a photon has lapped the planet's equator 7 times and is already a third of the way through its 8th lap. In 1 second, light could travel from the surface of Earth to the surface of the Moon and back again with distance to spare. The Moon sits 384,000 kilometers away. Light crosses that gap in roughly 1.25 seconds. The astronauts on the Apollo missions took 3 days to cover the same distance. Light does it in the time it takes you to say the word one. In 1 second, a beam of light would cross the entire continental United States roughly 1,000 times. Coast to coast, back and forth, 1,000 round trips, all while you are still deciding whether to exhale. This is not fast the way a jet is fast, or fast the way a bullet is fast. Those things are fast relative to human experience. Light is fast relative to the structure of the universe itself. There is a difference. A jet breaks the sound barrier. Light defines the upper limit of what causality permits. Nothing with mass has ever travelled at light speed. Nothing with mass ever will. Light does not hold the record. Light is the ceiling. 1 minute of light travel covers just under 18 million kilometers. 1 hour stretches that to 1,080,000,000 kilometers. In a single day, light races across 26 billion kilometers, a figure so large it has already left every human reference point behind. But a light year is not 1 day. It is 365.25 days, 8,760 hours, 525,960 consecutive minutes of movement at the absolute maximum velocity the laws of physics permit. When you complete the full calculation, 1 light year equals 9,461,000,000,000 kilometers. Not because someone chose a convenient round number, because that is simply what falls out when you multiply the speed of light by the number of seconds in a year. Here is where the scale becomes almost comedic. If you climbed into a car and drove at highway speed 120 kilometers per hour and pointed yourself in the direction of an object exactly 1 light year away, the drive would take approximately 9 billion years. Not 9 million, 9 billion. The Sun is 4.5 billion years old. The Earth is 4.5 billion years old. You would need to have started your journey before the solar system existed, driven without stopping through the entire history of life on Earth, past the first oceans, past the first fish, past the dinosaurs, past every human civilization ever, built, and you still would not have arrived yet. You would need another 4.5 billion years of driving after our sun burns out to finally reach your destination. 1 light year, 1 unit, the smallest distance astronomers regularly discuss. So when a scientist stands in front of a camera and says the nearest star is 4.2 light years away, with the same casual tone one might use to say, the grocery store is 3 blocks down, what language are they actually speaking? What are they describing when they say that number as, though it requires no further comment, they are describing something the word distance was never designed to contain? And the most unsettling part is not the number itself. It is what lives inside it, because 1 light year is not only a measure of space, it is a measure of time. And that combination creates something far more frightening than any figure a calculator can produce. There is a way to make this real, not comfortable, not small, but real. And it starts with a marble. Imagine shrinking the sun down until it fits in the palm of your hand. A perfect sphere 1 centimeter across, warm, bright. The entire mass of a star that burns 4 million tons of hydrogen every second, compressed into something smaller than a grape. At that scale, where is Earth? Earth becomes a speck of dust, not a small pebble, not a grain of sand. A speck of microscopic dust, roughly 1/10 of a millimeter across, orbiting your marble sun at a distance of about 1 meter. Hold your arm out. That gap between your palm and your fingertips, that is where Earth lives. Jupiter, the largest planet in the solar system, becomes a peppercorn. A single black peppercorn orbiting 5.2 meters from your marble. If you place your marble on a table, Jupiter is somewhere across the room. Neptune, the outermost major planet, sits 30 meters away, about the length of a basketball court. If you stand at one end with your marble sun, Neptune is a speck near the opposite baseline. Every planet, every moon, every asteroid belt, every comet in the solar system, all of it fits within 30 meters of your hand. Now ask where 1 light year falls at this same scale. 68 kilometers away. Not 68 meters. 68 kilometers. In Vietnam, that is further than the distance from the center of Hanoi to Vinh Phuc province. In this scale model, you hold the sun in your palm. Neptune sits 30 meters away at the other end of a basketball court, and 1 light year stretches to a point somewhere past the provincial border. Between your marble and that distant point, 68 kilometers of space, there is nothing. Not a single marble. No other sun sitting anywhere along that route. No planets orbiting something in the middle. No asteroid belts you might stumble across. Nothing. Just 68 kilometers of pure, featureless, absolute emptiness. The nearest star system to our own Alpha Centauri does not appear until nearly 290 kilometers away at this scale. Farther than Hanoi to Vinh. Farther than Hanoi to Thanh Hoa. This emptiness is not merely a visual absence. It is a physical reality with consequences. The space between stars is the most thorough vacuum nature produces. In the interstellar medium, the technical name for the thin fog of matter between star systems, the average density of matter falls to roughly 1 atom per cubic centimeter. One single atom floating alone in a cube of space the size of a sugar cube. Compare that to the air surrounding you right now. Every cubic centimeter of the atmosphere you are breathing contains approximately 25 billion trillion molecules. The interstellar void is roughly 25 quintillion times less dense than the air filling your lungs at this moment. To replicate interstellar conditions in a room, you would not merely need to pump out the air. You would need to remove every molecule from the room, then from the building, then from the entire city block, and keep going until your evacuated zone spanned the volume of a small country, and you would still only be approaching the density of what sits between stars. Occasionally, a stray hydrogen atom drifts through. Rarely a dust grain smaller than a bacterium tumbles past ancient debris from a dead star scattered across light years of nothing. That is the entire inventory of what a spacecraft would encounter during an interstellar crossing. No fuel to harvest along the way, no gravitational waypoints to adjust course, no landmarks to confirm position. The void offers nothing. It only takes. A spacecraft traveling through interstellar space is not like a ship crossing an ocean where currents and winds and coastal features define the journey. It is more like a stone thrown into a void with no walls, no floor, no ceiling, and no way to know if you are still moving in the right direction unless you brought everything you need to find out. If the entire solar system, 8 planets, hundreds of moons, an asteroid belt, a cloud of comets, 4.5 billion years of gravitational architecture is just 1 grain of sand sitting at one end of a 68-kilometer empty road, what kind of distance are we actually talking about? And this is only the distance, the measurement, the gap between here and there. The real problem, the one that has humbled every engineer, physicist, and dreamer who has ever confronted it, honestly begins the moment you ask a single follow-up question. How long would it actually take to cross it? On September 5th, 1977, a rocket lifted off from Cape Canaveral, carrying a spacecraft the size of a small car. Its name was Voyager 1. Its mission was to fly past Jupiter, past Saturn, photograph their moons, measure their magnetic fields, and then keep going outward beyond the edge of everything humanity had ever mapped into the space between stars. It worked. Spectacularly. Voyager 1 flew past Jupiter in 1979. It swept past Saturn in 1980. It sent back images that rewritten entire chapters of planetary science. It discovered active volcanoes on Io. It revealed the intricate structure of Saturn's rings in detail no telescope had ever achieved. And then, with the gravitational slingshot of those two gas giants stored in its velocity like a gift it could never return, it kept going. Past Neptune's orbit, past the heliopause, the boundary where the sun's solar wind finally loses its grip on the interstellar medium. Out into the void, Voyager 1 is currently the most distant human-made object in the history of our species. It has been flying for 47 years without stopping, without refueling, without a single engine burn since its planetary encounters. It travels at roughly 17 kilometers per second faster than any bullet, faster than any aircraft, faster than anything the majority of humans will ever conceptually grasp as a real speed. In 47 years of continuous flight at 17 kilometers per second, Voyager 1 has covered approximately 0.0027 light-years. Not 2.7% of a light-year, 0.27%, less than 0.3 of 1%. Let that land. 47 years ago was 1977. That was the year Star Wars appeared in cinemas for the first time. Since that moment, humanity has gone from no personal computers to smartphones more powerful than the entire computing infrastructure that sent Apollo to the moon. We went from typewriters to the internet, from film cameras to artificial intelligence that generates images from text, from pages to devices that hold the sum of human knowledge in a shirt pocket. In 47 years, the pace of human technological transformation has been so rapid that someone who fell asleep in 1977 and woke up today would not recognize the world they returned to. And Voyager 1, the fastest object our species has ever sent into deep space, boosted by the gravitational pull of two of the largest planets in the solar system, has covered less than 0.3% of 1 light-year. Now do the arithmetic forward. If Voyager 1 had been aimed directly at a target exactly 1 light-year away on the day it launched, and if it could somehow maintain its current speed indefinitely, no slowdown, no fuel loss, no mechanical failure, it would arrive at that destination in approximately 17,600 years. That means it would reach its target around the year 19,600 in the Common Era. Think about what existed 17,600 years ago. There was no Rome. There was no Egypt. There was no writing, no agriculture, no city of any kind anywhere on Earth. Human beings were living in small nomadic groups, hunting megafauna across landscapes that have since been swallowed by rising seas. The entire recorded history of human civilization, every empire, every language, every invention, every war, every work of art, would not begin for another 12,000 years after Voyager's hypothetical departure. And Voyager would still be in transit. New Horizons, which delivered the first close-up photographs of Pluto in 2015 and currently travels at roughly 14.5 kilometers per second, would need approximately 20,700 years to cross. 1 light-year. The Parker Solar Probe, which holds the record for the highest speed ever achieved by a human-made object, reaches approximately 176 kilometers per second during its closest approaches to the Sunday. At that peak velocity, 1 light-year would require roughly 1,700 years, but that speed lasts only minutes during the brief window when the probe skims the sun's corona. In open interstellar space, without the sun's gravity pulling it inward and then releasing it like a slingshot, the Parker Solar Probe would travel far slower. The peak speed is a momentary flash, not a sustainable cruise. The pattern across every spacecraft humanity has ever built is identical. Whether you measure in thousands of years or tens of thousands, the destination does not change. 1 light-year remains catastrophically, almost mockingly out of reach. So, is this a technology problem? A funding problem? A matter of building a bigger rocket, finding a better fuel, investing more resources in the next generation of propulsion? Or is something else happening here? Something structural? Something that does not yield to incremental improvement? Something written into the fabric of physics itself, rather than into the limitations of any particular engine. This is not an engineering gap. This is not a problem that more money or ambition or decades of development can close by iteration alone. The obstacle is a mathematical equation, one derived in 1897, one that has governed every rocket ever built, and one that no spacecraft in history has ever escaped. There is something about 1 light-year that almost nobody discusses. Something that makes the distant stranger more disorienting, and in some ways more frightening than any travel time calculation. A light-year is not only a measure of distance, it is a measure of time. When you observe an object sitting 1 light year away, the light entering your eyes or your telescope did not leave that object moments ago. It left 1 year ago. It has been traveling across 9,461,000,000,000 kilometers of empty space for an entire year before it reached you. What you see is not the object as it is. It is the object as it was 12 months in the past. You are not looking into space. You are looking into history. Scale this outward, and the effect becomes staggering. The sun you see in the sky right now is the sun as it existed 8 minutes and 20 seconds ago. If the sun were to suddenly vanish at this precise moment, you would not know for another 8 minutes and 20 seconds. You would continue feeling its warmth, continue seeing its light, continue living under its glow, while in reality, the star itself would already be gone. The North Star Polaris, which sailors have navigated by for centuries, sits approximately 430 light-years from Earth. The light reaching your eyes when you look at it tonight left that star in the year 1595, during the reign of Elizabeth I of England, decades before the telescope, was invented more than a century before Isaac Newton was born. You are not seeing a star, you are seeing a 430-year-old postcard. The Andromeda Galaxy, the nearest major galaxy to our own floats, 2.5 million light-years away. Every photograph ever taken of Andromeda is a photograph of how that galaxy looked 2.5 million years ago, before Homo sapiens existed. Before the first stone tools were shaped, when our ancestors were creatures no one today would recognize as fully human. We have never seen Andromeda as it currently is. We never will. By the time its light reaches us, the information it carries is already ancient beyond any meaningful human reference. This is the hidden dimension of the light year. It is a timestamp as much as a distance. Every observation is archaeology. Every telescope is a time machine, running in only one direction deeper into the past. Now apply this to a spacecraft. Imagine a probe launched toward a destination 1 light-year away. By the time it reaches the halfway point, 4,730,000,000,000 kilometers from Earth, any signal transmitted from mission control takes 6 months to arrive. The probe's response takes another 6 months to return. 1 full year passes on Earth between the moment a question is asked and the moment its answer is received. If a sensor malfunctions, if a navigation correction is needed, if something unexpected appears in the probe's path, Earth cannot respond in any time frame that matters. The instruction to adjust course would arrive 6 months after the moment the adjustment was needed. For a mission traveling at conventional speeds where the journey itself spans thousands of years, this communication delay renders real-time control not merely difficult, but conceptually meaningless. The civilization that launched the probe could rise and fall multiple times before a single round-trip message completes its journey. The spacecraft must think for itself, decide for itself, survive for itself, because the world that built it cannot reach it in time to help. But the isolation runs deeper than communication delays. A crew aboard that vessel would exist in a kind of temporal no man's land. News from Earth would arrive months late. Their replies would be received long after the original context had dissolved. They would be physically present in the universe, alive and functioning, yet informationally severed from every institution, relationship, and moment of history that defined them. The separation is not only spatial, it is temporal. They would occupy the same universe as the people they left behind, but an increasingly different version of its timeline. The real wall around 1 light-year is not made of distance. It is not made of vacuum or radiation, or the hostility of the interstellar medium. It is made of silence. The absolute physics-enforced silence that falls between any traveller and their origin, the moment the distance becomes large enough that the speed of light itself can no longer bridge the gap in time. When the universe itself cuts every line of communication, when the laws of physics make real connection structurally impossible, can any civilization truly send something across that silence and call it a mission? The answer lies in what our technology can actually do. And the numbers, when you look at them honestly, without the comfort of optimism or the buffer of vague future promise, will force you to reconsider everything you thought you knew about humanity's place in the cosmos. Every single object humanity has ever sent into space, every satellite, every probe, every crewed capsule, every space station component, every telescope, every rover, reached orbit or beyond, using the same fundamental mechanism. A chemical rocket. Burn propellant, expel hot gas backward through a nozzle, move forward. That is the entire principle. Isaac Newton described it in 1687, and 3 centuries of engineering refinement have not changed its essential nature by a single degree. The principle is elegant. The limitation hiding inside it is brutal. A chemical rocket engine works by releasing the energy stored in molecular bonds, the invisible electrical connections between atoms inside the fuel. When hydrogen and oxygen combust inside the engine chamber, those bonds break and reform into water vapor, releasing energy that heats the gas to extreme temperatures and drives it out the nozzle at high speed. The faster the exhaust leaves the nozzle, the more thrust the engine produces. Simple. The best chemical engines ever built, the RS-25 engines that powered the space shuttle, burning liquid hydrogen and liquid oxygen, push their exhaust out at approximately 4.4 kilometers per second. That is the ceiling. Not the ceiling of current technology, the ceiling of chemistry itself. The energy available inside chemical bonds has a fixed upper limit written into quantum mechanics and molecular physics. No exotic fuel mixture, no advanced combustion geometry, no clever engineering innovation can meaningfully exceed 4.4 kilometers per second of exhaust velocity. The molecules simply do not contain more energy than that. Now here is where the tyranny begins. In 1897, a Russian schoolteacher named Konstantin Tsiolkovsky derived an equation describing the relationship between a rocket's exhaust velocity, its fuel mass, and its final speed. The equation is not complicated to state, but its consequences are devastating. The relationship between fuel and speed is not linear, it is exponential. And exponential growth in the wrong direction is the definition of a trap. Think about doubling your car's speed on a highway. Going from 60 to 120 kilometers per hour requires more fuel, yes, but roughly twice as much. The relationship is close to linear. Push harder, go faster, pay proportionally more. A rocket does not work this way. If you want to double a rocket's final velocity, you do not need twice the fuel. You need approximately 9 times the fuel mass relative to your payload. If you want to triple the velocity, you need not 3 times the fuel, but roughly 9,000 times the payload mass in propellant. Every additional increment of speed costs exponentially more mass in propellant, and that propellant itself needs to be accelerated, which requires more propellant, which needs to be accelerated, which requires still more propellant. Watch what happens as the target speed climbs. To reach 10 kilometers per second, roughly what Voyager 1 achieved, you need about 9.7 kilograms of fuel for every kilogram of payload. Manageable, expensive, but achievable. This is the regime of interplanetary probes. Double the target speed to 20 kilometers per second, and the fuel requirement per kilogram of payload jumps to approximately 94.6. Push to 40 kilometers per second, and it leaps to nearly 9,000. Attempt 100 kilometers per second, still less than 0.03% of light speed, and you need more than 7 billion kilograms of propellant for every single kilogram of payload. That exceeds the total mass of every object humanity has ever launched into space multiplied by roughly 1 million, and 100 kilometers per second is still cosmically trivial. It is nothing. At that speed, crossing 1 light-year still requires 30,000 years. This is the tyranny Tsiolkovsky described, not a soft limitation that better engineering can gradually erode. A mathematical wall with vertical faces. Doubling speed does not double fuel requirements, it squares them. Tripling speed does not triple requirements, it cubes them. The relationship is unforgiving, and it applies equally to every rocket ever built, regardless of how sophisticated the engineering becomes. If doubling fuel always doubled speed, humanity would have reached the stars decades ago. So what, in the structure of physics, actually prevents that? What forces the exponential relationship instead of the linear one? The answer is that every gram of fuel you add must itself be accelerated to the same final velocity as the payload. Fuel is not free mass, it is burden. And the burden of carrying fuel to accelerate, fuel to carry more fuel, spirals outward in a curve that bends toward impossible long before the target speed reaches any meaningful fraction of the speed of light. Chemical propulsion is not a flawed technology waiting to be improved. It is a fundamentally, structurally, mathematically incapable technology for the task of crossing interstellar distances. magnificently suited to reaching orbit, to traveling between planets, to everything humanity has accomplished in space so far, and completely categorically outmatched by 1 light-year. But humans are not the kind of species that reads an equation, accepts defeat, and goes home. They looked at the ceiling, chemistry imposed, recognized it was real, and reached for something 1 million times more powerful. The first move beyond chemistry seems obvious in hindsight. If the problem is that chemical bonds do not contain enough energy, find a process that releases more energy per kilogram of fuel. Nuclear fission releases roughly 1 million times more energy per unit mass than chemical combustion. That is not a modest improvement. That is a civilizational leap in energy density. Nuclear thermal propulsion takes the most direct approach. Replace the chemical combustion chamber with a nuclear fission reactor. Instead of burning hydrogen and oxygen together, pipe pure hydrogen through a reactor core, heat it to extreme temperatures using nuclear energy, and expel it through the nozzle. The exhaust velocity roughly doubles compared to the best chemical engines, from 4.4 kilometers per second to approximately 8 or 9 kilometers per second. Doubling exhaust velocity matters. For solar system missions, it means carrying significantly less propellant to achieve the same delta V, which translates to smaller vehicles, lower launch costs, and faster transit times to Mars and beyond. The United States built and tested nuclear thermal rocket engines during the 1960s under a program called NERVA, Nuclear Engine for Rocket Vehicle Application. The engines worked. They produced real thrust. The technology was proven, then shelved for political and budgetary reasons. But plug the improved exhaust velocity into the Tsiolkovsky equation and ask what it means for 1 light-year. The travel time drops from 13,000 years to roughly 7,500 years. Better. Still utterly useless for any purpose connected to human life. Nuclear electric propulsion takes a different path. Use a reactor to generate electricity feed, that electricity into an ion drive, and expel charged particles at exhaust velocities of 30 to 50 kilometers per second, or potentially far higher with advanced designs. The trade-off is thrust. Ion engines produce tiny amounts of force measured in millinewtons rather than meganewtons. They cannot launch from a planet's surface. They accelerate glacially, but they can thrust continuously for months or years, gradually accumulating velocity with extraordinary efficiency. A well-designed nuclear electric system might eventually reach 100 or 200 kilometers per second. At that speed, 1 light-year still requires 1,500 years. Then someone asked a genuinely different question. What if instead of a controlled, steady energy release, you used the most concentrated burst of energy the physical world permits? What if you detonated nuclear bombs? Project Orion was born at General Atomics in San Diego in the late 1950s, and it was the most audacious engineering proposal in the history of spaceflight. The concept was as direct as it was startling. Mount a massive steel plate at the rear of the spacecraft, the pusher plate. Eject a nuclear device behind the plate. Detonate it. The pulse of superheated plasma slams into the plate, transfers its momentum through a system of enormous shock absorbers, and the ship lurches forward. Then eject another device. Detonate it. Repeat hundreds of times, thousands of times, riding a continuous chain of nuclear explosions across the solar system and beyond. It sounds like the premise of a science fiction film. It was in fact the serious work of some of the most brilliant engineers and physicists of the 20th century. Among them was Ted Taylor. Taylor was not a theorist working at a safe distance from real weapons. He had personally designed both the smallest fission device and the most efficient fission device in the entire United States nuclear arsenal. He understood nuclear explosions the way a master carpenter understands wood grain at the level of intuition built from years of direct consequential work. And Ted Taylor, after examining Orion in detail, concluded that it was the most physically viable path toward interstellar travel that physics permitted. When the person who knows more about nuclear weapons than almost anyone alive tells you an idea is sound that carries weight, the numbers justified his conviction. With optimized nuclear pulse units, Project Orion vehicles could theoretically reach between 3 and 5% of the speed of light. At 3%, 1 light-year takes approximately 33 years. At 5%, roughly 20 years. For the first time in this entire analysis, the travel time had dropped into the span of a single human life. Not a comfortable life aboard a spacecraft, but a life nonetheless. An astronaut departing at 30 could arrive before turning 60. The strangest footnote of the 20th century may be this: while the entire world was gripped by terror that nuclear weapons would end human civilization, a group of engineers in San Diego were quietly calculating how those same weapons could carry human civilization to the stars. The identical technology pointing in two completely opposite directions. The bomb that threatened everything and the engine that could reach everything, separated only by the question of which way you aimed it. Project Orion did not fail because the physics was wrong. The physics was sound. It died because in 1963, the Partial Test Ban Treaty prohibited nuclear detonations in outer space, in the atmosphere and underwater. A vehicle that required detonating hundreds of nuclear devices on or near Earth's surface to build initial velocity was now illegal under international law. Not impossible, illegal. If a technology is physically viable but legally prohibited, not because science condemned it, but because politics rightly prioritized survival over ambition, what does that reveal about the nature of the barriers standing between humanity and the stars? The barriers were never only in the physics, and even if Orion had survived 20 years, it's still a long journey with no ability to slow down at the destination. Reaching 1 light year in a human lifetime required a fundamentally different philosophy, one that abandoned the idea of carrying energy entirely. Every propulsion system examined so far shares one architectural assumption so fundamental it feels invisible. The spacecraft carries its own energy source. Whether that energy is locked inside chemical bonds or nuclear pulse units, the vehicle must haul it along, accelerate it, and spend it over the course of the journey. The Tsiolkovsky equation governs this architecture without mercy, ensuring that the relationship between fuel mass and final velocity grows exponentially punishing. But what if the spacecraft carried no fuel at all? What if the energy stayed home, fixed to the ground, anchored in orbit, connected to a power grid, and only the spacecraft traveled, pushed from behind by a beam of concentrated light? This idea has existed since at least the 1960s, when physicist Robert Forward first proposed using laser beams to accelerate interstellar light sails. For decades, it remained a thought experiment, elegant in concept, impossible in practice for want of sufficient laser power. Then, in April 2016, an initiative called Breakthrough Starshot announced a funded serious engineering study of exactly this concept, backed by $100 million in initial funding. The underlying physics is not exotic. Photons carry momentum. When a photon strikes a reflective surface and bounces back, it transfers twice its momentum to that surface. Once on arrival, once on departure. A single photon's momentum is absurdly small, but concentrate enough photons into a coherent beam and aim them at a surface that is simultaneously highly reflective and extraordinarily lightweight, and the accumulated force becomes real and measurable. This is not purely theoretical. In 2010, the Japan Aerospace Exploration Agency launched a spacecraft called Icaros Interplanetary Kitecraft, accelerated by radiation of the Sunday. Icaros deployed a 14-meter square solar sail in deep space and was measurably accelerated by the pressure of sunlight alone. No engine, no propellant, just photons pushing on a thin membrane. The effect was small but unambiguous. Radiation pressure is real, confirmed, and operational. Breakthrough Starshot scales this principle to an extreme. The proposed system involves a phased laser array, producing a combined beam power of 100 gigawatts, roughly the total installed electrical generation capacity of France, focused onto a sail approximately 4 meters in diameter. The sail is attached to a payload chip, a gram-scale integrated circuit containing a camera, a communication laser, a processor, and a power source. Total mass of the entire spacecraft between 1 and 10 grams, depending on the design iteration. Under 100 gigawatts of focused laser illumination, this near-weightless vehicle would experience acceleration exceeding 10,000 times Earth's gravity for several minutes, reaching approximately 20% of the speed of light before the beam loses focus, and the spacecraft coasts onward. At 20% of light speed, 1 light year passes in 5 years. 5 years. The number lands differently than everything before it. 5 years fits inside a doctoral program, inside a presidential term, inside the span of time between one Olympics and the next. For the first time, interstellar distance starts to feel like something that could exist on a human planning horizon. The physics supporting this is entirely known science. No exotic particles, no speculative fields, no undiscovered phenomena. Radiation pressure has been measured in laboratories. Photon momentum transfer is textbook physics. Everything about Starshot relies on principles confirmed long before the project was conceived. But confirmed physics and buildable hardware are separated by a gap that swallows entire careers. 100 gigawatts of phase-coherent laser power does not exist. The most powerful continuous lasers currently operating produce tens to hundreds of kilowatts, roughly 6 orders of magnitude below the Starshot requirement. The sail material must reflect more than 99.99% of incident light at the operating wavelength at a thickness thinner than half a human red blood cell. While surviving acceleration forces 10,000 times Earth's gravity, no material manufactured at scale today achieves this. At 20% of light speed, interstellar dust grains that would barely scratch a spacecraft at conventional speeds become projectiles, carrying the kinetic energy of artillery shells. And when the spacecraft arrives, it cannot stop. The laser is 100 million kilometers behind. There is nothing ahead to push against. It screams past its target in minutes and disappears into the void forever. The only system capable of crossing 1 light-year within a human lifetime carries a payload measured in grams, cannot decelerate, and survives its journey by pure statistical luck against dust grain bombardment. If the only way to arrive in a reasonable time is to arrive too fast to stop, too small to carry anything meaningful, and with no way back, does that qualify as arriving at all? This is the point where physics stops being an ally and becomes something more complicated. Because the moment speed climbs high enough, the universe does not merely present engineering challenges. It changes the rules of the game entirely. For the entire history of human spaceflight, physics has been generous. Isaac Newton's equations force equals mass times acceleration. Every action produces an equal and opposite reaction. Kinetic energy scales, with the square of velocity, have described the motion of every spacecraft ever built with extraordinary precision. The Voyager probe's trajectories were calculated using Newtonian mechanics and verified to match predictions within meters over billions of kilometers. The equations work. They have always worked. For everything humanity has ever built and flown, the Newtonian framework is not an approximation. It is reality. But Newton's equations are themselves an approximation, one that holds perfectly at low velocities and begins to crack as speed approaches a meaningful fraction of the speed of light. Above roughly 10% of light speed, the cracks widen into chasms. Above 50%, the Newtonian framework does not merely become inaccurate, it becomes deeply structurally wrong. What replaces it is special relativity. Albert Einstein published the theory in 1905, built on 2 postulates that sound almost trivially simple and produce consequences so counterintuitive that even professional physicists sometimes stop to reconsider them. The laws of physics are identical for all observers moving at constant velocity, and the speed of light in a vacuum is the same for all observers regardless of their motion. From those 2 statements, everything else follows, including the fact that as an object's velocity increases toward the speed of light, its resistance to further acceleration, what physicists call its effective inertia, increases without limit. At rest, accelerating 1 kilogram by 1 meter per second squared requires exactly 1 newton of force. At 10% of light speed, the force required is slightly higher. The difference is negligible. At 50%, the effective inertia has increased enough to notice. At 90% of light speed, pushing the same object requires 2.3 times more force than at rest. At 99%, 7 times more. At 99.99%, 70 times more. And at exactly the speed of light, the required force becomes infinite. Not very large, not beyond current engineering, infinite. No finite amount of energy delivered over any finite period of time can accelerate an object with mass to the speed of light. This is not a technology limitation. It is a geometric property of space-time. Translate this into energy costs for a real spacecraft. A probe massing 1,000 kilograms, roughly the size of the Curiosity Mars rover, accelerated to 10% of light speed, requires kinetic energy equal to approximately 1/4 of Germany's total annual electricity production. Every wind turbine, every solar panel, every power plant in Germany running for a full year directed entirely at accelerating one single small probe. At 20% of light speed, the energy rises to roughly the annual electricity production of France. At 50%, the figure approaches 2.4% of total global annual energy consumption, now scaled to a crewed vessel. A minimal spacecraft capable of keeping human beings alive across an interstellar crossing, life support, radiation, shielding food, water, recycling, medical supplies, habitat space, redundant systems, would mass at minimum 1 million metric tonnes. Accelerating that vessel to 50% of light speed requires approximately 24,000 years of current total global energy production. Every power plant on Earth running continuously for 24,000 years to push one ship. Antimatter offers the highest theoretical energy density physics permits. When 1 gram of antimatter meets 1 gram of ordinary matter, they annihilate, completely converting 100% of their combined mass into energy, equivalent to 43 kilotons of TNT. In principle, a few tens of kilograms of antimatter paired with equal ordinary matter could push a spacecraft to significant fractions of light speed at a mass ratio the Tsiolkovsky equation would find perfectly acceptable. In practice, the total quantity of antimatter produced by every particle accelerator on Earth since the positron was discovered in 1932 amounts to approximately 20 nanograms, 20 billionths of a gram. Producing 1 gram using current technology would cost approximately $25 trillion and consume the entire electrical output of the United States for roughly 1 year. And storing antimatter requires magnetic containment systems where any contact with ordinary matter, any contact at all for any duration, triggers immediate annihilation. Antimatter is the perfect fuel on paper. It is also the most expensive, most dangerous, and least available substance in the history of human technology. Antimatter is the perfect fuel on paper, the way a dream house is perfect on paper when the price tag equals the GDP of the entire planet for 300 years, and dropping the key destroys the neighborhood. There is one gift relativity offers in return for all it demands: time dilation. As a spacecraft accelerates toward the speed of light, time passes more slowly aboard the ship than for observers back on Earth. This is not illusion or perception. It is physically real, experimentally confirmed, measured in atomic clocks, flown on aircraft, and in the extended lifetimes of subatomic particles streaking through the upper atmosphere. At 99% of light speed, the crew of a spacecraft experiences approximately 7.5 weeks of subjective time for every year that passes on Earth. A 1 light-year crossing that takes slightly over a year in Earth's reference frame lasts roughly 7.5 weeks for the people aboard. The distance has not changed. The vacuum is still 9,461,000,000,000 kilometers wide. But the crew's lived experience of the journey compresses dramatically. The seduction of this is real. Cross 1 light year at 99% of light speed and arrive feeling as though you were in transit for less than 2 months. At 99.9%, the crossing feels like barely over 2 weeks. The stars are no longer decades away. They are subjectively close if the speed can be achieved. But time dilation does not reduce the energy cost by a single joule. The 24,000 years of global energy production required to push a crewed vessel to 50% of light speed does not shrink because the crew experiences the journey as shorter. The physics of energy does not care about subjective experience, and the human cost of time dilation is something no engineering solution addresses. A crew returning from a relativistic crossing of 1 light year arrives home younger than the people they left behind. Friends have aged. Children born after departure are adults or elderly. Everyone they knew intimately has moved through years of experience the travelers never shared. The world has changed in ways they could not participate in and cannot fully understand. They are not merely returning from a long trip. They are returning from one version of history to a different one, and the version they left is gone. This is not science fiction. It is the mathematical consequence of special relativity applied to human relationships, and no amount of engineering improvement makes it negotiable. The universe offers speed, it charges time, and the transaction is final when the physics of motion starts extracting payment not in money or fuel, but in the people you love and the world you belong to. the story of crossing 1 light-year stops being a story about technology. It becomes a story about what it means to be human. And that story leads somewhere even the most honest physics calculations cannot fully prepare you for. In 1964, a Soviet astronomer named Nikolai Kardashev asked a question that no one had framed quite that way before. Not which civilization is most intelligent. Not which has the most advanced mathematics or the most sophisticated philosophy or the most complex social structures. Those questions he recognized were interesting, but ultimately unmeasurable from the outside. The question he asked was simpler, harder, and more revealing than any of those. Which civilization commands the most energy? Kardashev proposed a scale with 3 levels. A Type 1 civilization controls and utilizes the total energy resources available on its home planet. Every watt of solar energy striking the surface, every joule of geothermal heat rising from the core, every erg of wind and tide, and chemical potential the biosphere can provide. For an Earth-like world, this amounts to approximately 10 to the power of 17 watts. A Type 2 civilization controls the total energy output of its parent star. For a Sun-like star, that figure is approximately 3.8 times 10 to the power of 26 watts, roughly 2 billion times the power available to a Type 1 civilization. The concept most commonly associated with this level is a structure surrounding the star and capturing most or all of its radiated energy. A Type 3 civilization commands the energy output of an entire galaxy, approximately 10 to the power of 36 watts for a galaxy like the Milky Way, a level so far beyond current human capability that describing it strains the vocabulary of ambition. Where does humanity sit on this scale right now? Approximately 0.73. Not Type 1, not even close to Type 1. Humanity currently harnesses roughly 1.8 times 10 to the power of 13 watts from all sources. Combined every fossil fuel plant, every nuclear reactor, every hydroelectric dam, every solar panel, every wind turbine on the entire planet. That is approximately 1/10,000th of the energy available to a fully realized Type 1 civilization. Map those numbers onto what crossing 1 light-year actually demands. Accelerating a crewed vessel to 50% of the speed of light requires energy that a Type 1 civilization could generate in approximately 2.4 years. A Type 2 civilization could produce the same energy in a matter of seconds the way a modern power grid powers a city block for an afternoon. Humanity at its current level would need 24,000 years of total global energy production. The gap between what physics requires and what humanity currently produces is not a factor of 2 or 10 or 100. It is a factor of 10,000. Space telescopes are currently searching actively, systematically, for evidence of structures around distant stars that might indicate a civilization harvesting stellar energy at Type 2 scale. Astronomers have catalogued unusual stellar light curves, monitored energy outputs that deviate from stellar models, and flagged candidates for further observation. The search is serious, ongoing, and funded. So far, no confirmed detection, no unambiguous signal, no structure that cannot be explained by natural astrophysical processes. That absence is itself data. It is not proof that such civilizations do not exist, but it is a fact that sits in the room and refuses to leave. Humanity is currently standing at 0.73 on a scale where the interstellar threshold begins somewhere around Type 1 to Type 2. In the universe's version of an exclusive venue with a strict entry policy, we are outside on the pavement in shorts and sandals, while the sign at the door reads, "Minimum dress code, suit and formal shoes." We are not close to meeting the requirement. We are not even sure we are in the right part of town. And if a Type 2 civilization can launch an interstellar mission with roughly the same energetic effort as a modern nation launching a weather satellite casually, routinely, without mobilizing planetary infrastructure, then the universe, they should be full of their signals, their artifacts, their presence. So why across 13.8 billion years of cosmic history, with hundreds of billions of stars in this galaxy alone, has no civilization apparently crossed that threshold in any way we can detect? This is the moment when 1 light-year stops being a problem of engineering It becomes a question about the survival rate of intelligence itself everywhere for everyone across all of time. In the summer of 1950, during a casual lunch conversation at Los Alamos, National Laboratory physicist Enrico Fermi looked up from his food and asked a question that has occupied serious scientists ever since. The Milky Way is approximately 13 billion years old. It contains somewhere between 200 and 400 billion stars. Surveys of nearby stars suggest that the majority of them host planetary systems, and a significant fraction of those systems contain planets in the habitable zone. Not too hot, not too cold, with conditions that could in principle support liquid water and complex chemistry. Given all of that, Fermi asked, where is everybody? The silence is not a small puzzle. It is a profound one. Consider what 1 billion years of head start means. If a civilization emerged anywhere in the Milky Way just 1 billion years before humanity and developed technology at even a fraction of the pace human civilization has managed in the last few centuries, they would have had enough time to colonize every star system in the galaxy multiple times over. Even traveling at 1% of the speed of light, a civilization expanding outward from a single origin point could reach every corner of the Milky Way in roughly 10 million years. 1 billion years would give them 100 such journeys. The galaxy should be overflowing with the evidence of civilizations that arrived here long before our sun even formed, and yet, nothing. No confirmed signals, no megastructures, no artifacts in the asteroid belt, no unexplained energy signatures from the galactic core. The universe across every wavelength we can observe maintains a silence that grows more puzzling the longer we look. In 1998, economist Robin Hanson gave this puzzle a name and a framework: the Great Filter. Something in the path from simple chemistry to interstellar civilization is extraordinarily difficult to pass through, so difficult that almost nothing makes it. The filter exists because the math demands it. If interstellar civilizations were common, we would see them. We do not see them, therefore something filters them out. The only question, and it is perhaps the most consequential question in all of science, is where in that path the filter sits. If the Great Filter is behind us, then humanity has already survived the hardest part. Perhaps the emergence of complex life from simple chemistry is the filter. Perhaps the development of eukaryotic cells or multicellular organisms or language or technological civilization. Perhaps one of those transitions is so improbable that it almost never happens, and we are the extraordinary exception. If that is the case, the path ahead is open. The silence of the universe is the silence of a galaxy where we are genuinely remarkably rare, and the future belongs to whatever we choose to build. If the Great Filter is ahead of us, if the hardest step is still to come, somewhere between where humanity stands now and the interstellar civilization we imagine, then the silence of the universe carries a different message entirely. It means that most civilizations reach roughly our current level of development and then fail to advance further. Not through dramatic extinction events necessarily. Not through asteroid impacts or nuclear wars or engineered plagues, though those remain possibilities. Simply through failure to cross the energy threshold that 1 light-year represents. They plateau. They stagnate. They turn inward. And eventually, they end, as all things end, without ever sending a single gram of matter to another star. This is where 1 light-year connects to the largest question in astronomy. The same physics that governs the energy requirements for crossing this distance governs that requirement for every civilization anywhere, built from any chemistry operating under any social structure in any corner of the cosmos. The Tsiolkovsky equation does not negotiate based on biology. Special relativity does not offer discounts for civilizations that have been polite or ambitious or virtuous. The energy cost of crossing 1 light-year is the same for every species that has ever looked up at a night sky and wondered what lies beyond. 1 light-year is not humanity's private challenge. It is a universal threshold, a filter encoded in the geometry of space-time itself, applied with perfect impartiality to everything that has ever achieved the level of technological development required to ask the question. And the silence surrounding us suggests that most who reach the question never find the answer. If the cosmos is littered with civilizations that ran out of time, will, or energy before crossing that first light-year, what does that mean for the choices humanity is making right now? Strip away every number, Set aside the Tsiolkovsky equation, the Lorentz factor, the energy budgets, the travel times, the propulsion architectures. Remove every technical detail that has filled this journey from beginning to end. What remains at the absolute core of the problem is not a physics question. It is a question about what humanity actually is. 1 light-year is a test, not of intelligence. The species that mapped the human genome split. The atom detected gravitational waves from colliding black holes 1 billion light-years away, and taught machines to reason is not failing for lack of cleverness. Not of technological capability, the engineering achievements of the last century have been genuinely extraordinary, genuinely humbling, genuinely unprecedented in the history of life on this planet. The test 1 light-year administers is different from both of those. It tests something rarer, more fragile, and far less certain. It tests whether a civilization can coordinate across timescales longer than any individual life, any government, any institution, or any era of history. Every great thing humanity has ever built was completed within decades by a fraction of the total human population. The pyramids at Giza took roughly 20 years to construct. The great medieval cathedrals of Europe, the longest of all traditional human construction projects, spanned a few generations at most. The global electrical grid, the internet, the International Space Station, all accomplished within a century by institutions that rose and fell and were replaced by others in the process. Every achievement in the history of human civilization was finished within a time frame that a single human being could at least in principle witness from beginning to end. Interstellar travel demands something humanity has never done. Not a bigger version of what it has already accomplished, but a qualitatively different kind of commitment. Centuries of sustained, coordinated effort directed toward a goal that the generation laying the foundation will never see completed. The engineers who design the first interstellar propulsion systems will die long before those systems are tested. The scientists who calculate the optimal trajectory will never know if their numbers were right. The politicians who allocate the first resources will be forgotten by the time those resources produce results. Every person who contributes to the project must do so, knowing with certainty that they will not live to see its conclusion. The longest continuously operating human institutions are certain religious organizations and a handful of universities, some of which have maintained unbroken operation for approximately 1,000 years. The energy infrastructure required for interstellar travel may demand coordinated commitment, lasting 10 times that duration. 10,000 years of sustained investment in a single goal, maintained across political upheavals, economic collapses, generational shifts in values, and the ordinary entropy that dissolves human institutions over time. The physics does not care about election cycles. It does not adjust its requirements based on quarterly earnings reports or shifting cultural priorities, or the entirely understandable human preference for immediate results over distant promises. It simply states its terms. Can you produce enough energy? Can you sustain the effort long enough? Can you build institutions that outlast not just individual lives, but entire eras of history? And yet, this is not a reason for despair. It is something far more useful than despair. It is clarity. Humanity has crossed thresholds that looked impossible from the outside many times before. Not because the obstacles were small, they were not small, but because clearly seeing the size of an obstacle is the first step toward taking it seriously enough to actually address it. The ancestors who first crossed oceans did not know what lay on the other side. They knew the size of the water and they built boats accordingly. The engineers who first split the atom did not know what the energy would become. They knew the energy was there and they found ways to reach it. Every single propulsion concept examined in this story, from chemical rockets to nuclear pulse drives to laser sails to fusion engines, was developed by people who understood clearly that the problem was nearly impossible and pursued it. Anyway, the roadmap exists. The physics is known. The obstacles are identified, named, and measured with precision. That is not a minor accomplishment. In the history of the universe, the number of things that know anything about their own limitations is extraordinarily small. 1 light-year is not a destination. It never was. It is a mirror. And the mirror is asking a question it has been asking since the first human being looked up at a night sky and felt the pull of something beyond the horizon, not whether the journey is possible. The physics has already answered that yes, in principle, with sufficient energy and sufficient time. The mirror asks something harder, something that no equation can answer and no telescope can observe. If humanity knows exactly how high the wall is, knows exactly what it would take to build the ladder, knows exactly what the first rung requires, is it the kind of species that begins to climb? 9,461,000,000,000 kilometers, just 1 light-year. The first rung of a ladder with no visible top, and we, a species that has existed for 300,000 years, that has practiced science for 400 years, that has built rockets for less than 100 years, have already measured that first rung down to the last centimeter. Not climbed it, not yet, but measured it. And, in the full sweep of cosmic history across 13.8 billion years of stars burning and dying, and the vast majority of matter doing nothing at all, a thing that can measure the distance to the stars and understand why it cannot yet reach them is already something remarkable, already something that should not exist, already something the universe did not have to produce. The abyss is 1 light-year wide. We are only just beginning to understand what it would mean to cross it.